So in this segment, we'll talk about how to find the in-plane elastic shear modulus G12 for a unidirectional lamina. So to review, we already have done the derivation for E1, E2, nu12, and G12, and now we're going to concentrate on G12. Again, I'm not going to go through the full derivation of G12, but to mention that the way we're going to go about doing so is to apply shear stress in the 1-2 plane. This is the 1-2 plane. So you have 1 here, 2 here, and 3 is through the thickness. So you're going to apply the shear stress and you're going to figure out what the corresponding shearing strains are. And based on that, you'll be able to relate the in-plane shear modulus to the shear modulus of the fiber in the matrix and the amount in which they are mixed in. And this is what you're going to get. You're going to get the inverse rule of mixtures here, that shear modulus is given by this particular relationship given there. Now let's go and look at an example. So if somebody asks you to find the in-plane shear modulus of glass epoxy lamina with 70% fiber volume fraction, as we have been doing, we will use the properties from table 3.1 and 3.2. We do not get the properties of the shear modulus properties of the fiber in the matrix directly from table 3.1 and 3.2, so we'll have to calculate that. So we know the Young's modulus and the Poisson's ratio. We will use this relationship, which is true for isotropic materials. So keep in mind that you can only use these relationships for calculating the shear modulus if the fiber in the matrix are isotropic. We have, like graphite is transversely isotropic, so we may have to use that with caution when we find the shear modulus of the fiber. So we have this relationship for the isotropic material of glass, and we get this. This is the Young's modulus of the fiber. This is the Poisson's ratio of the fiber, and we get the shear modulus of the fiber here. Same thing here, we have Young's modulus and Poisson's ratio of the matrix given of the epoxy. We are able to find out what the shear modulus of the matrix is. Now we are set. How are we set? Because we know that we have an inverse rule of mixtures right here. 1 by G12 is equal to VF by GF plus VM by GM. We already know the volume fraction of the fibers. Volume fraction of the matrix is simply 1 minus the volume of the fraction of the fibers. So this is the shear modulus of the fiber, shear modulus of the matrix, and we will get what the shear modulus, in-plane shear modulus is of the unidirectional composite. Now, one of the things which we saw in the calculation of E2 as well is that the experimental data points do not match very well with the mechanics of materials approach. So here is in-plane shear modulus being plotted as a function of fiber volume fraction. You're finding out they are there so far as the experimental results are concerned, and this is the inverse rule of mixtures formula. But if we concentrate only on the fiber volume fraction between 0.4 and 0.75, you are finding out, hey, these are the experimental data points, and this is what you get from the mechanics of materials approach. So there's a big difference between the two. And how do we account for that? And that's something which we'll do in the next section. So let's look at the summary of the mechanics of materials equations for elastic moduli of a unidirectional composite material. Is that we get the rule of mixtures for the elastic modulus E1, we get the rule of mixtures for the major Poisson's ratio, then for the transverse Young's modulus E2 and the in-plane shear modulus G12, we get the inverse rule of mixtures. So the formulas are pretty simple, and we should be able to use them in order to calculate our formulas for E1, E2, nu12, and G12, as you saw that in chapter 2, how we use these properties to do the macromechanical analysis of a lamina. And that's the end of this segment, guys.